Well, students, we are in the third chapter of our course, which is on numerical linear algebra. In this chapter, so far, we have covered direct methods and also we have studied matrix norms. We are now into the third part of this chapter, which is on iterative methods. Recall that in the first part of this chapter, we have studied basically two methods, Gaussian elimination method and some methods which are categorized as LU factorization methods. These methods gives exact solution when floating point approximation is not involved in the computation. Such methods are generally called direct methods. Well, although they give exact solution when infinite precision computation is applied to them, nevertheless, they are very costly in terms of time taken to compute the solution of this system. Therefore, they are less preferred in applications, especially in those applications where the linear system is very large. In such cases, people generally prefer what is called iterative methods. They give only approximate solution even if you compute with infinite precision, because they are built by introducing certain approximation to the system at the mathematical level. Therefore, they have errors coming from that approximation. Plus, of course, when you go to put them on the computer, like the direct methods, they also are exposed to floating point approximation and the error due to that, which we generally call as arithmetic error. So iterative methods are prone to have mathematical errors as well as arithmetic error. Nevertheless, they are preferred in large scale scientific computing because they are much cheaper when compared to direct methods in terms of time taken to compute the solution of the linear system. There are two fundamental iterative methods that we will initially start with. They are Jacobi method and Gauss-Seidel methods. Let us start with Jacobi method. If you recall, when we were introducing LU factorization method, we said that there are basically three types of systems which doesn't need elimination procedure. One is the diagonal matrix system, another one is the upper triangular matrix system, and finally the lower triangular matrix system. Out of these three, the most simplest one is the diagonal matrix system, in which we don't even need to go for either forward substitution or backward substitution. The solution comes directly, right? So just imagine if every system that we deal with is a diagonal system, then we don't need to go for the elimination process, which is the most costliest part in the direct method, right? Now, keeping this in mind, let us try to explore the idea of how to build a basic iterative procedure. Write your given matrix A in the form D minus C, where D is the diagonal part of your matrix A. That is, if you are given A as Aij, where I varies from 1 to n, which corresponds to rows, and j varies from again 1 to n, which corresponds to columns, then Aii will be the diagonal entry of the ith row, right? So in that way, D is the diagonal part of the matrix A, and whatever remains elsewhere, we can combine them and call that matrix as C, in such a way that A can be written as D minus C. This we can do for any given matrix A. Once you have written your A in this form, then the system AX is equal to B can be written as D minus C X is equal to B, right? Therefore, dx can be written as cx plus b, in which you can see that the left hand side is in the diagonal form. Therefore, a non-diagonal system is now put in a form where the left hand side is in the diagonal form. Now, are we done that we can directly go for getting the solution of this system without going for any elimination? The answer is no, because the right hand side is not fully known to us. Well, we only made the left hand side in the diagonal structure. In that process, the right hand side became unknown to us. If by any chance you know completely the right hand side, then what remains is a diagonal system, right? Because D is diagonal. But unfortunately, the right hand side is not fully known to us because X is sitting here. But can we somehow make it known? Well, what you do is choose a vector of your choice, whatever it may. It's okay. You can even take 0 vector. You choose a vector arbitrarily and plug it on the right hand side. Now you see, since you plugged in something which you chose, which is known to you, the right hand side became fully known to you. And what remains now is the diagonal system, and you can directly find the value of X such that dx is equal to the right hand side which is given like this, not the right hand side that you want. Solution of this system X may not satisfy your original system Ax is equal to B, right? Therefore, we cannot claim that we have solved our original system. Nevertheless, we have surely got some vector, say x1, such that dx1 is equal to cx0 plus b. x0 is the vector that you chose as per your choice, whatever it can be. Then you plugged it into the right hand side and got the vector x1 by solving this system, which is just a direct process. We don't need to go for any elimination process to get x1. So you got this x1 by solving this system. And now once you have x1, you can again plug in on the right hand side. Instead of x0, you can plug in x1 now and then solve this system with this as the right hand side. And whatever comes out as the solution of that diagonal system, you can call it as x2. Now you go on doing this. In general, you got a vector xk, you plug it on the right hand side here and solve this diagonal system, and whatever solution comes out of this diagonal system, you call it as xk plus 1. So in that way, what we got is a sequence of vectors we are getting out of this procedure, where k varies from 0, 1, 2 and so on, where 0th level we have chosen the vector x0, and from that onwards x1, x2 are computed by plugging in the previous level vector on the right hand side, making your system as a fully diagonal system, and then directly getting the solution of that diagonal system. We are generating these vectors xk for any k equal to 1, 2, 3 and so on. Now, if D is invertible, I can also write this system in this form just for the convenience. Now you see, you have a nice formula for computing xk plus 1. That is given by bxk, where b is d inverse c and the vector small c is d inverse into the right hand side vector b. So once you are given a, you know what is d and what is c. Therefore, you know what is b. Also, you know what is the right hand side vector b, and that gives you what is the vector c. Therefore, right hand side is fully known to you, and hence every term in the sequence xk can be explicitly computed by choosing the initial one, that is x0, as per your choice, whatever it may, it's okay. Once you choose and fix, correspondingly, you will get a sequence. Okay, so this procedure is what is called Jacobi method. What is the input of this method? Well, it is A, B, and X naught, right? These are the inputs. Once you have A, your method will compute what is B. And once you have small b, that is the right hand side, it will compute what is small c. And then it sets this formula and give you as an output xk, which is a sequence of vectors. Well, if you go to implement it on a computer, you cannot go on generating xk for any k. You have to stop it somewhere, and thereby you have on a computer, you have finitely many terms of this sequence. Now the question is, what is the connection between this sequence and the solution of my original system in which I am actually interested in? See, I am interested in finding solution of this linear system, right? What Jacobi method gave is this sequence. What is the connection between these two is the question. Well, the natural idea is to see whether this sequence is going to converge. If it converges, say xk is converging to some, say, x, will that x satisfy this system? That is the next question. So we have two questions in hand. One is the sequence that I generated through this procedure, is that sequence going to converge? Is the first question. The second question is, if it converges, will the limit of that sequence be the solution of my linear system? Well, before going to answer these questions, let us try to put the formula that we have derived so far in a nice closed form, at least for a 3x3 system, because most of the time in examples, and more precisely from the examination point of view, mostly we will work with 3x3 systems. Therefore, it's always comfortable to write this formula more explicitly in the case of 3x3 system. That will be more handy for us. So let us consider this 3x3 system, which is not necessarily a diagonal system. Now, what you will do as a first step, you will keep all the diagonal part on one side and push the non-diagonal part on the other side. That is, in the first equation, you keep a11 x1 on one side, push rest all on the other side. b1 minus a11 x2 minus, sorry, a12 x2, a13 x3, right? Similarly, from the second equation, keep the diagonal term on the left hand side and push everybody else to the right hand side. That is a21 x1 minus a23 x3. Similarly, in the third part, you keep a33 x3 on the left hand side and write the right hand side as b3 minus a31 x1 minus a32 x2. Now what you do, if a11 is not equal to 0, then this can be brought to the other side and made 1 by a11 of the entire thing. Similarly, a22 is not equal to 0, then you can do the same idea here also. And similarly, if a33 is not equal to 0, then you can push this to the right hand side. And that gives me this formula where x1, x2, x3 are calculated explicitly, provided your right hand side is known to you. Otherwise, x1 is written in terms of x2 and x3. And similarly, the other guys, where you don't know them, right? Therefore, strictly speaking, this is no way better than the original system, but our idea is something different. What is that idea? We have rewritten our system like this. This is something like what we have written. X is equal to B times X minus C, right? Where B is nothing but D inverse C, and C, the small c, is D inverse the right hand side vector B, where D is the diagonal matrix and C is such that A can be written as D minus C, right? These are the basic ideas out of which we have derived this formula. And this is nothing but rewriting this system. Ax equal to B is just rewritten in this form. Okay, both are equivalent. Similarly, this in 3 by 3, it is just a rewritten. Okay, we have not done anything, and this is just the same as this in the case of 3 by 3 system. Now comes the idea, you choose any vector, remember any vector, which is called initial guess to us, any vector, and plug in that vector on the right hand side of each of these equations. And thereby we are getting values for x1, x2, and x3. Well, don't call this as solution to your original system. It may not be the solution for your original system. Nevertheless, you can call it as, say, x11, x21, and x31. Okay. Once you have this vector, again plug in this vector on the right hand side and get another vector which you will call as x12, x22, x32. Like that, you will go on generating the sequence of vectors using this formula. You see, now this is explicitly written for 3 by 3. Similarly, you can write for 4 by 4 system and so on. This is exactly the same as what we wrote in the previous slide. Xk plus 1 is equal to B times xk plus C, right? Sorry, this is plus C. Previously, I think I wrote minus C. This is plus C. And that gives you, in the case of 3 by 3 system, this simple explicit formula. And this is called Jacobi method. If your given system is a 3 by 3 system. And the sequence thus generated is called the Jacobi iterative sequence, or simply Jacobi sequence. This method comes under a class of methods called iterative methods. How these methods look like? Well, you have some equation. That equation you should first rewrite in a form, say x equal to t of x, where t is some function. Then you start with some known quantity. It may be that you choose by yourself or it comes through some other way. Whatever it is known to you. Then you put it on the right hand side. That is, you just apply t on it. And whatever comes out, you call it as x1. And then you again go to put t on x1. And whatever value comes out of that, you call it as x2. And you keep on doing that. And in that way, you generate a sequence. Such methods are called iterative methods. You can clearly see that the Jacobi method is an iterative method, where t is given by this right hand side quantity, right? So in that way, Jacobi method is a iterative method. In our course, we will also see many iterative methods. Next, let us come to this interesting question of the sequence that we generated using Jacobi iterative procedure, whether this sequence is going to converge or not. And if it converges, is it going to converge to the exact solution of your linear system? Well, the answer for this question is not that simple. One needs to make some analysis on it. Why it is not that simple? Let us see an example. Consider building the Jacobi iterative sequence for this linear system. and let us see whether that sequence is going to converge or not. How will you make Jacobi sequence for this? Well, it's very easy. You keep this term on the left hand side, take this term to the right hand side, and finally this 6 you divide on both sides. That gives you the first equation. And similarly, the second equation, you have to keep the second term because that is the diagonal term, and you do the same idea. You get the second equation, and similarly you keep this term on the left hand side, take others on the right hand side, and finally divide both sides by -4, and that gives you the third one. So this is the Jacobi iterative sequence. You start with any x0, you keep generating the terms of this sequence like this, right? And it goes on using these formulas. Now what we will do is we will start with some x0 and generate this sequence. Before that, let us also see what is the exact solution of this system. Up to 6-digit rounding, the system solution is given by this vector. And now let us start our initial guess with the trivial choice of 0 vector. Then x1, well, what I'm doing is I'm putting on the right hand side, I'm putting 0, 0, 0 vector and finding x1 using this formula, right? And that gives me x1 like this. You can just compute and see. Once I get x1, I again plug in x1 on the right hand side of the Jacobi sequence and get x2, and again plug in x2 on the right hand side of the Jacobi sequence, get x3, and so on. Now you can see that after every sequence computation, let us see how we compare our terms with the exact solution. Well, looks very nice. You can see that more or less you are going closer to the solution, right? And x5 is given like this. We are very close to the solution, at least up to 2 digits. If you do rounding, you can see 0.44 is coming here. Therefore, -0.44 is very close to your solution. Up to 2 digits rounding, you are getting it. And 0.34 again is pretty good, and 0.15 again pretty good. Up to 2-digit rounding, you are getting the solution. So it gives us a feeling that if you go on doing this computation further, we may converge to this exact solution. And in fact, it is true. If you just put it on a computer and generate it x6, x7, and so on, and see that it converges nicely, in the sense that as you go on computing more and more terms, your terms will go more closer and closer to the exact solution x. Now let us take another system, and the system is given like this. If you recall, this system is exactly the same as the previous system. Only thing is, in the previous system, this was in the first position and this equation was in the second position. You can go back and see that 6x1 plus x2 plus 2x3 equal to -2x is now in the first equation, whereas x1 plus 4x2 plus 0.5x3 equal to 1 is the second equation. And we saw that by starting with 0 vector, we are pretty converging at least up to 5 terms, and one can check that by going to further terms, we go more closer and closer to the exact solution. Whereas the system is same, only thing is I just shuffled these two equations. Therefore, the solution will not change, because by interchanging 2 rows, the solution is not going to change, right? Let us do the same Jacobi sequence computation with the same initial guess. Before that, let us also note that the solution is not going to change. The solution remains the same. But now the Jacobi sequence formula changes, because previously we had a different formula. Now we had a different formula. Remember, when this was in the first equation, then this was kept on the left hand side and these two were taken to the right hand side, right? Now you will keep this on the left hand side because your equation is in the second position, whereas these two terms will be pushed to the right hand side, and thereby your second equation is like this. Similarly, in the previous iteration, this was kept in the left hand side and these two were pushed to the right side, right? Now this will be kept on the left side and these two will be pushed to right side. Therefore, your Jacobi iterative sequence formula is different. System is same, formula is different. You start with the same initial guess 0, 0, 0. And let us compute now the iterative sequence terms with this formula and see how they go. The first term in the sequence looks like this. Second term is like this. Just go back and recall what is the solution. The solution is minus 0.44, 0.34 and 0.15 up to 2 decimal digits. Now you have x3 like this. You can see that you are going away from your solution, right? The fourth term is like that, fifth term is like that, and so on. So you clearly see that up to at least fifth term, you are pretty far away from the solution. Whereas in the previous case, we were approaching the solution as you go on computing the higher and higher terms in the sequence, which is not happening now. In fact, you can see that as you go on computing, say x6, x7, the sequence just goes rapidly away from the solution and it gives bigger and bigger numbers in the coordinates. And that shows that your sequence seems to be diverging. So it's not really clear whether your Jacobi sequence is going to converge or not. So the first question that we raised, whether it will always converge or not, is not true. There are systems for which the Jacobi sequence converges and there are systems for which the Jacobi sequence doesn't converge. So first job for us to identify which all the sequence for which Jacobi sequence converges and for what all the sequence it doesn't converge. Okay. And then we will worry about if the sequence converges, will the limit be a solution to your original linear system? That's the next question that we have to answer. But the first question itself is not seems to be that easy because we have seen that the system is same, but the behavior is different. By just shuffling one equation with the other, we just see just the opposite behavior in the Jacobi iterative sequence.